All right, in number 3, we're going to try these same sort of tricks on a semicircle. I think I'm going to go ahead and slice horizontally again. It's totally up to you. You can slice vertically. It'll work just fine. But I really like just making it all the way across. And I'm going to call this a delta H again. And then you also have the choice. Delta H is a little vertical distance, so H should be measuring a vertical distance. You can choose top or bottom. Since I did bottom as my fixed point last time, I'm going to say I'm measuring how far my slice is from the top of this shape. So I want to find the area of that little slice, and the area is going to be whatever this width is times delta H. So my big task here is to figure out how to find that formula that relates H to W in a semicircle. Within triangles, it's similar triangles. Within a semicircle, there is actually a triangle, but it's not similar triangles that helps us out. So what I want to recognize here, the really key thing, is that the determining factor about this shape is its radius. And I can tie this radius to my slice by making a line from the middle of the circle to one of the outer edges of my slice. And from there, I can extend this into a triangle. The bottom of this triangle, don't get mixed up. Sometimes people want to say that's your radius as well. It's not. The radius has to go from the very center of the circle to the outer edge of the circle, and this bottom corner of your triangle is not the middle of the circle. So dead center, not center horizontally or vertically. Okay, since I don't know that, I need to think a little bit. So I don't know that this bottom of my slice is 5, but I did name the width of my slice W, so I could call that W over 2. And then the trick here is not similar triangles, it's a Pythagorean theorem. We know that the equation for a circle is x squared plus y squared equals r squared, so that's that Pythagorean theorem that's always built into a circle. We're going to see similar things for spheres as well. So I could say that h squared plus w over 2 squared, which will become a w squared over 4, is equal to 25. Which means w squared over 4 is equal to 25 minus h squared, which means w squared is equal to 4 times 25 minus h squared. And you can distribute that 4 in, but I'm just spotting that if I square root this, I could actually extract that out and say that w is 2 times the square root of 25 minus h squared. Okay, so when I go back up here, I can say that my single slice has area 2 times the square root of 25 minus h squared times a delta h. To get the total area, I'm going to need to integrate to add up all the slices. So I'm integrating 2 times the square root of 25 minus h squared. Technically up above it would still be an h sub I. dh, so that's the length and width of my rectangle. And then my h is how far from the top the slice is. So I should start at the very top, which is going to be an h equals 0. And then I want to stop at the bottom of the semicircle, which is going to be 5 inches down from the top. So that radius does apply there, because this is starting at the very center of the circle. So we're going to go from 0 to 5. And this might look a little messy. I would say this is a great candidate for a trig substitution. So let's say that we're going to replace h with 5 sine theta, which means dh is going to be a 5 cosine theta d theta. And that will turn this into 2 times, what do we have under there? The square root of 25 minus 25 sine squared theta multiplied by a 5 cosine theta d theta. Let's see, so I'm going to pull that 10 out in front. And then underneath the radical, we want to spot that that's going to be 25 times 1 minus sine squared theta, which is the same as 25 cosine squared theta. What did I already snag? I already snagged that. And then we'll have an extra cosine theta d theta. And then the square root of the 25 cosine squared theta is just going to leave us with a 5 cosine theta. Okay, so I have a 50 times the integral of cosine squared theta d theta. And then if you remember your power reducing formulas, you can use them. If you don't, we could do a quick integration by parts where we say our u is equal to cosine theta, our du, derivative of cosine, is a minus sine theta d theta. Our dv is also a cosine theta, which means our v, oh, and there's the d theta, is a sine theta. So we have 50 times u times v, which is cosine theta sine theta, minus the integral of v du, so it's going to be plus a sine squared theta d theta. There we go. And then, let's see. Didn't leave myself enough room for this messy one. Okay, so I think I'm going to jump down and do a little bit of side work. So what we've got right now is that the integral of cosine squared theta is equal to, here I am not leaving myself enough room again. Cosine squared theta is equal to cosine theta sine theta plus the integral of sine squared theta d theta. So this is going to end up being a solve. And the trick is that this looks like one of those where we should do it again, but doing it again will actually make everything fall apart. So what we want to do is say this is the same as the integral of 1 minus cosine squared theta d theta. So use a Pythagorean identity to get back where you started instead of using by parts again. Okay, so now we can say the integral of cosine theta d theta is equal to cosine theta sine theta plus theta minus the integral of cosine squared theta d theta. Okay, so all I've done there is split the integral up. The integral of 1 is theta. And then what I'm going to do now is add this integral of cosine squared theta to both sides. And say, now I have 2 times the integral of cosine squared theta d theta equals cosine theta sine theta plus theta. And I just need to divide by 2. So I have a 1/2 cosine theta sine theta plus theta over 2. And we could throw in a plus c, but we were actually working on a definite integral, so it's not really going to matter. So I'm going to go back up now that I did all this big side work, and I'm going to fill that in. Okay, so we were back here. So I'm actually going to erase what's in the brackets now that we're all the way done with it. We're going to say that that integral of cosine squared theta was equal to 1/2 cosine theta sine theta. I think it was a plus we were on, right? Yeah, plus theta over 2. And I said we were definite, but I think I've lost those limits. We're going from 0 to 5. Oh, that's why I've lost them. Hold on. We've changed through variables since then. Okay, so let's look at what we have. We have h equals 5 sine theta which means sine theta is equal to h over 5. So theta is inverse sine of h over 5. So if, what did we start with? If h is starting at 0, then theta is going to be the inverse sine of 0, which as I'm erasing it, I can say is actually also 0. If, where are we going now? We're going to 5. So if h is 5, then theta is equal to the inverse sine of 1, which is going to be pi over 2. When is sine equal to 1? Whoa, that was a crazy wiggle. Sine is equal to 1 when we're at the top of the unit circle, pi over 2. Okay, so now let me carry that down. Zero to pi over 2. Okay, so when I plug in pi over 2, I get 1/2 cosine of pi over 2. So again, think about your unit circle. Pi over 2 is right at the top, is 0. So that's actually going to wipe that out completely. So we're just going to be left with the pi over 2 divided by 2, so pi over 4. And then when we plug in the 0, we get 1/2 sine of 0 is 0, so that's actually going to go away again. And then we get 0 over 2, so actually this is it, which we can reduce to 25 pi over 2. Okay, so kind of big messy work to get through this one. Last thing I think I want to point out here is, again, I am making you do something that might feel kind of silly. I promise it's going to be useful. We can check our answer really easily because this is half of a circle. So we want 1/2 pi r squared. Our radius is 5 inches. So there it is, 25 pi over 2. So all that mess, and we are in fact right. Yay!